3, 2, 1. And now you can take over. Thanks again. Welcome, Nora.
Thank you. Okay, so now I get to do the exciting screen sharing. Okay, it should be this way.
I'll monitor the chat if anyone has any questions that I can have, but we also will leave some time for questions at the end as well.
Okay, hello. So today I'm going to be talking about noise that we make and its effects on fish and the kind of ecosystems and systems that they're a part of. So before I begin, I always like to acknowledge and thank all of the people that made this research possible. I could not have done it without many, many other people helping and supporting me, as well as lots of funding resources and universities that allowed me to do this research, but also the many peoples on whose land I conducted these experiments, I currently reside and work, and I grew up on, and whose relationships to this land continue and are very important. And I think that this is particularly important when we're talking about species that are existing in these lands, species that still today have these deep relationships with the original people that lived here. So I think it's definitely very important to kind of think about that and remember that we are on these unceded territories. Okay, so generally, when I talk to my friends, sometimes families, sometimes just other random people, about what they think about when they think about the ocean, what does the ocean sound like when you're in it? And more often than not, what people say is, "Oh, Nora, it's gonna be so quiet and serene and just like, you know, a beautiful abyss of nothingness and joy." And you're just like, okay, I'm glad that you think that. But for many people who study the ocean in any capacity, they very quickly realize that the ocean is actually a quite noisy place. And this noise comes from a whole bunch of different sources. So you have things that we call geophony. So these are types of noise that are generated by kind of non-biotic or non-living natural processes. This is things like the wind hitting the surface of the water, rain, thunderstorms, rock slides, earthquakes. All of these things create noise in the ocean. Then you have what most people think about when you talk about natural noises in the ocean, and that's biophony. So that's all of the biotic organisms making noise. This can be things that we think are very intentional, like whale song and fish grunts and shrimp snaps, or it can be kind of incidental noise, things like animals chewing their food or simply swimming through their environment. Um, and this generates all sorts of different types of noises. Now, of course, these types of noises have been around forever, but there's new noise that is going into the ocean, and that's anthropophony. And that's all the noise that we make. So this is everything from vessel traffic to the noise that installations like wind farms make. This is also the noise of any type of exploration or attempting to see under the water. This is explosions. This is sonar. And also the actual construction, any type of construction that goes on near oceans, you tend to have things like pile driving, where you're making a huge amount of noise. And we know from studying lots of different animals that noise in the ocean is not a great thing. And we also know that it's something that is continuing to expand and continuing to get louder and louder as humans do more in the ocean and go more places in the ocean. Now, historically speaking, when we think about the animals that people have been studying in the ocean and how noise is affecting them, we tend to think of the big charismatic ones because these are the ones that we started seeing the effects on first. This is the things like the killer whales that we live near and that we adore. This is like pinnipeds, seals, dolphins, all of these big animals that we're actually seeing these changes in their behavior. Um, but that's not the only animals in the ocean that we've actually started studying. In many more recent years, instead of studying just mammalian species, we've started to focus a lot on fish. And we focus on fish for a couple of different reasons. First, because we should really be studying as many different things as we can in order to understand our impacts, but also because truthfully, fish are part of our economy. We eat them, we need them for all sorts of different stuff. And so we start to get very interested in things that could possibly start causing declines or things that may change how easy they are to catch. And we found a lot of stuff about fish. So many people have asked the question of how noise impacts fish. And we know that noise can actually injure and kill fish. If they're too close to a really loud noise source, this can absolutely just kill a fish. But we also know that there's non-lethal effects. So lots of different types of ways that noise can just affect fish in bad ways. It can increase the stress that they're experiencing, which can cause susceptibility to disease to increase. We know that noise can cause fish to change where they're swimming, for example. They might swim farther away from the noise source. They might swim deeper in the ocean. We know that it can change how easy it is for them to eat, how easy it is for them to detect predators. So we know that noise can affect fish in many, many different ways. And while this is really important, I'm always much more interested about the consequences. So what is actually happening if we're affecting a fish? Not just what's the fish doing, but what does this actually mean for the systems that this fish lives in? And so to ask this question, I really wanted to think about, well, what type of fish am I thinking about? And it's not just any old fish. What about something like these guys, like forage fish? Now, forage fish are really interesting because unlike most other species, they exist in this really interesting position in their ecosystem. So there's many, 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 many very small species that everything eats. And there's many, 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 many really big species that eat everything else. But there aren't very many species in between. And that's where the fish sit. They sit in this like little tiny choke point in the ecosystem of the food chain, where that chain goes. So they're this little center bit that everything flows through in order to go to the top. And so potentially something that impacts a forage fish could impact a huge amount of the food chain and affect many, many other species. So instead of just asking, how does noise impact fish? We might want to ask, how does noise impact forage fish? Okay, so now we're getting closer to this idea of the consequences of noise on particular species. But this still is leaving something out. While we're still asking about forage fish, we still aren't quite getting to the entire crux of the matter. And that's because we're leaving out these guys. We're leaving out the predators. And so instead of just asking about the forage fish themselves, instead of just saying, like, how are all the different ways that noise might affect the forage fish, we want to focus in. And we want to focus in specifically on this idea of how they might be interacting with their predators and how this might be echoing through the food chain. So instead of just asking how noise might impact forage fish, we might ask how noise impacts forage fish and how might these impacts affect their quality and their availability to their predators. So how is this going to change the relationship that they have with their predators and therefore the rest of the ecosystem? So now we have our question. So the next step is to choose a study system. So we chose the Pacific Sandlands, and these are a pretty, in some ways, standard forage fish. Like many forage fish species, these guys tend to swim around in the open water in these really, really large schools. They're relatively small fish. And we know that these fish in particular, at least in this area around Victoria and in the Salish Sea, are incredibly important for breeding seabirds. We know that in bad years, seabird fledglings don't do as well. They tend to not fledge or survive as well as years with really high amounts of Pacific sandlands. So in the spring and summer, like herring, like lots of other forage fish species, they just roam around in the open waters or in the deeper waters in these big schools. And you'll see, all of the seagulls going down, and you'll see pinnipeds and all sorts of other mammals coming up and eating. Everything eats these fish. But the really interesting thing about these fish that other forage fish don't do is that these guys bury in the sand. And so this is particularly interesting because it means that they can be removed as a prey source for many of their predators when they do this behavior. Now, we know that these fish will bury in the sand occasionally, just randomly throughout the day. We know that they bury in the sand overnight. And we also know that during the winter time, when food resources are really scarce, they actually go dormant. So they go and they bury in the sand for 2 to 3 months at a time. And it's during this time that they develop their gonads. So basically the entire breeding population goes dormant over winter and then comes out and spawns in the spring. So we have our species. Next, we need to choose, well, what sound are we talking about? What are we actually talking about when we're thinking about how anthropogenic noise or human-generated noise is affecting these fish? And we thought, well, why choose one sound? Let's test a couple of sounds. So for one sound environment that we wanted to create, we had silence. And this was just our control. This allowed us to understand what they did without any negative effects of noise. Then we had a consistent system. And so this was a wind farm, because wind farms tend to generate very consistent noise as the wind just keeps those rotors going. And so this was a noise that we created, this environment had 12 hours of wind noise, 6 days a week. No, sorry, yes, 6 days a week. Then we had a variable sound environment, and this was boat traffic. So this was a combination of boat traffic that you would hear kind of really far away, so shipping noise, kind of like background road noise kind of stuff. And then you would have actual ships passing in front of the hydrophone or the microphone, which all comes from Victoria Harbor. And so this was ferries, this was little zippy boats, this was all these other little types of boats as well that would pass by the microphone. So it would be quite variable in when they happened. This played for approximately 6 hours a day for 4 days a week. Then finally, we had our intermittent sound environment, and this was pile driving. And so to mimic how pile driving often happens, we actually only played back pile driving for 1 hour at a time. And this was over 4 hours a day. So we had 4 hours of these 1 hour bouts. And we only played this 2 times a week. So this was very variable, just would suddenly happen and then go away. Now, to be able to actually control this type of sound environment, to actually test how this noise was affecting these fish, we had to bring the fish into captivity, because there's just no way we can really control these environments or even actually effectively study these types of fish in the wild. So we caught sand lance, and the way that you do this is through seining, or at least the way that we did this was through seining. So you have a seine net. In this case, it's a hand seine, and this is Meredith White, one of the undergraduates that has worked with me. And she is the one who's done all of the actual processing and analysis for the behavioral aspect of this, which I'll get into later. But what we would do is we'd find schools of fish, we'd haul the nets up onto the beach, and then we'd take the fish and put them in coolers and transport them into their experimental housing. So this is the experimental housing. So each experimental sound environment had its own tank, so one big gray tank per environment. And then inside the tank, we had our school enclosures. So this was a kiddie pool filled with sand that they could bury into, and then it had aquaculture netting around the outside. So each school was contained to its own kiddie pool kind of vertical tube in the tank, but the water could move through and the sound could move through as normal. We also had an underwater camera as well as an underwater speaker, and this allowed us to both record the behavior as well as actually create the acoustic environment or the sound environment. This was all run with a dedicated computer for each experimental tank, and this automated both the video recording as well as the underwater speaker, so all of the sound environment. So each tank had its own special computer that created that sound environment for that tank. And then we also had a hydrophone just to kind of be able to double check that all the sounds were what they were. And we were hoping that these fish would make some type of exciting noise. Unfortunately, they do not appear to. So that was a bit of a bummer, but that's okay. Okay. So first, we're going to talk about this idea of fish quality. So this is how energy rich is this fish? If you're going to go out and catch, do you need to catch a whole bunch of fish, or do you only have to catch a few fish? And so this is this time during the spring and summer when the fish are incredibly accessible, and this is when all of the predators tend to be feeding on these fish. So we did these lab experiments in Friday Harbor at Friday Harbor Labs, which is part of Washington University, University of Washington, that would be UW. And this experiment ran for 10 days. So just because of logistics, we had two types of tanks. So we had two small indoor tanks. This was wind farm and boat noise. And then we had two large outdoor tanks, and this was control and pile driving. Okay, so in order to actually test quality in fish like this, we have to do what we call lethal measurements. So what we would do is we would euthanize a very small portion of the school for measurement, and then we'd let the rest of the school go back into the wild. Now, the first measurement is looking at the length-weight relationships. So we would take the fish and we'd measure their length and measure their weight, and that would give us the information for the length-weight measurement. So basically, for any given length, a heavier fish is going to be higher quality. So then we wanted to know how much energy every fish actually had, how many kilojoules of energy was in a fish. And so to do that, we calculate something called the ash-free dry weight. And to get this, you weigh the fish when it's wet, when it's fresh out of the water. Then you dry it in an oven for a number of days or weeks until it has a stable weight. So all of the water has evaporated, and then you weigh it again, and this is the dry weight. And then you put it in something called a muffle furnace, which reduces it to ash. And then this is the ash weight. So this is all the scales and um, bones and things that won't just evaporate off. And then that gives you, by comparing these together, that gives you something called the ash-free dry weight, which you put into a formula, and that gives you the energy density, which is the kilojoules per gram. So the actual energy that's in that fish. So what did we find? So on this graph, on the y-axis, on the vertical axis, you have weight in grams. And then on the x-axis, you have the standard length. So this gives us this weight-length relationship. And so the steeper the line, the more energy you have per length. So a steeper line is a better fish or a higher quality fish. So when we plot all of these fish and we plot these lines, we can see that the control is a little bit heavier per length than both the wind farm and the pile driving. So we are seeing that the controls are actually better quality than the wind farm and the pile driving, although the boat noise isn't really that different than the control. When we look at energy density, so we have the mean energy density in kilojoules per gram on the y-axis, and then we have our different treatments on the bottom, on the x-axis, we see that in general, control has more energy than either the wind farm or the boat noise, although it's not quite different from pile driving. So what does this tell us? Well, Pacific sandlands in noisy environments are basically poorer quality in the spring and summer. And this is true across all types of noise relationships. So it doesn't really matter what type of noise it is, either the length-weight relationship or the energy density shows that control fish are better quality. And so this means that Pacific sandlands that are living in noisy areas may actually just be poorer quality prey for their predators, which is a problem considering most of our Pacific sandlands live in the middle of shipping zones. Okay, so that tells us about the spring summer. What about the other time though? So if you'll remember, we have this dormancy period. Now, dormancy is really interesting because on the one hand, it could potentially act as a buffer. You could actually, because these fish are reducing their energy expenditure because they're going dormant, like a lot of animals do during hibernation, maybe they don't really get affected by the noise at all over winter. On the other hand, when you go into dormancy, you go into dormancy with all of the energy that you're going to have. And so if there is any effective noise, this could actually make things even worse for these fish because they have limited resources. So it could be a really good thing or it could be a really bad thing, and we simply don't know yet. So we decided to look at this dormancy period and see if noise was affecting this. So to do this, we caught fish in the Sydney Strait, right outside of Sydney. And we brought them into the aquatics facility for 10 weeks. So this was a good portion of their dormancy period. And we caught fish that were already dormant. So what did we find when we look specifically at this dormancy period? Same protocol. We have our weight-length relationships. Well, what we found is that there's not really a difference. Control fish are smack dab in the middle of all of these fish. So it looks like, at least for weight and length, that actually what we're seeing is that dormancy is acting as a buffer. It's protecting these fish from the effects of noise. When we look at the mean energy density, like with last time, we have energy density on the y-axis and our treatments on the x, we see that although there appears to be a little bit of a difference in wind farm, in general, these fish seem to be not really that much different from the control. And so it looks like this dormancy might actually be buffering them from the effects of noise. So dormancy may be basically being a safe time for these fish, even though they're still being exposed to noise. They're not really badly affected. And it could be because it's changing the stress relationship, or it's changing something about their behavior, or at least it's not changing these things when they're dormant. And so they're not being affected the same way. Okay, so that tells us a lot about the quality of the fish. So in the spring and summer, a lot of these predators may end up expending extra energy trying to catch these fish, or having to catch more fish because they're poorer quality. But in the winter, at least all of the fish that are going into dormancy, this breeding population, is probably going to be fine. And so all the fish that are going in should be coming out as per normal, even in really noisy areas. Okay, so now we know about the quality. What about the availability? So when we think about availability, what we're actually talking about is behavior. So we're going to be looking at the behavior of these fish as we recorded them in their tanks. So there's two particular behaviors we're going to be looking at, and this affects directly their availability to their predators. So the first is their burying behavior. Now, when we actually are looking at this, what we're looking at is, of all the fish in the school, how many of those fish are in the water and how many of them are in the sand. This is because the fish in the water are accessible to their predators. The predators can find and eat them. The fish in the sand are inaccessible. So if 90% of the fish are buried, well, that's 90% of the population that's completely inaccessible to their predators. If only 10% is buried, then most of the fish are available to their predators. So understanding how many fish are buried is really important. But I thought you guys would be interested in seeing a sand lance bury itself. So hopefully the video will transmit well online. But I will play this twice. The fish will be burying inside of that green circle, and I will tell you right after it happens, and then we'll watch it again, and I'll tell you right after it happens again. Okay, the fish just buried. So we're going to try that again. Okay, the fish buried again. So they're very fast when they bury. It's amazing to watch. So that's burying behavior. Now, the other behavior we're looking and we're interested in is startling behavior. So startling behavior is kind of, it's a pretty generic anti-predator behavior. Most animals do it to some extent. Fish do it in a very particular way. Basically, it's a burst of speed in a particular direction that's different than the speed that they were going before. And so what we'll see is this entire school will have a startle away from the camera and down towards the bottom of the tank. Right there. So you can see all of the fish just going really quickly. We'll play it again. So that's startling behavior. And the reason we're interested in startling behavior is because this basically tells us that the fish are aware that there's potentially predators around, and they're trying to evade or avoid that predation. So a fish that has a really kind of trigger response to startling or to predators will probably startle a lot. And it will mean that they're much more potentially able to evade predators, and so they're harder to catch. And so they're less available simply because they're harder to catch. Okay, so what did we actually find? So on the y-axis here, we're going to look at the proportion of the school in the water column. So this gets back to this idea of burying behavior, that if you have more fish, if you have a higher number in these graphs, you basically have more fish in the water column available to predators. Now, in all of these graphs, the one on the left is going to be boat noise, the one in the middle is pile driving, and the one on the right is wind farm. The triangles are going to be the silence, so they're the control. And then the filled in squares are when the days that the noise is on, and the empty squares are the days that the noise is off. But both are in the noise condition, so they're the noise environment. So when we look at the control, we see that over the days, the morning, afternoon, and evening, we see less fish in the water column. And this likely we think is happening because fish are getting enough food that they can spend the rest of the day and the night buried, and so they can avoid predators by burying. So we expect that over time, more and more fish eat enough that they can just bury and they can stay safe in the sand. So what do we see when we have boat noise? In the morning, we're not really seeing any differences between controls and these noise condition. In the afternoon, we're starting to see something quite different. And then in the evening, we're seeing something very similar to the control. So what about pile driving? Are we seeing a similar type of trend? And we are. We're seeing very similar things, although there's a bit of a flip between whether or not the pile driving is on or off in this type of relationship that we're seeing. However, when we look at wind farm noise, we're seeing something totally different. So we think potentially what might be going on here, and this would take a whole number of other experiments to actually suss out, but what we think might be going on is that in at least the boat noise and the pile driving circumstances, the fish may be getting distracted, something else might be going on, and it might be harder for them to get food, basically. We know that noise can act as a distractor, and it can lower the ability for individuals to hunt effectively or to process food effectively. And so it could be, at least in the boat noise in particular, that in this afternoon, they're having to increase their efforts in order to actually meet the food quota. But by the evening, they've all kind of met the amount of food that they normally would get, and so are able to bury. This is a little bit flipped in the pile driving, with the off days being the ones that are actually where we're seeing a lot of these fish in the water column. We're not entirely sure why that is. But we do think that also just increased stress, especially because pile driving is very intermittent, so it's not something you can get used to. So they might be a little bit more on edge because there's this thing that sometimes happens, but it doesn't always happen. And then with wind farm, we really don't know why it's so different. It could be that these fish are habituating in some ways, and so maybe they're more able to catch food, or it might be that this sound is so annoying and they can dampen it in the sound, and so they prefer to be in the sound. But as of yet, we are seeing these differences, but we're not entirely sure what's causing them. But it does mean that some of these fish, like the boat noise and pile driving fish, are more accessible in the afternoon than the control fish. And then some of them, like the wind farm fish, are less accessible. Okay, so what about startling behavior, right? So what about this anti-predator behavior where you're like really on edge and so you're responding really well to predators? So when we look at the control treatments, we see that there's not really a difference across the day, that you pretty much have the same number of startling fish. It doesn't matter what time of day it is, it's not very many. When we look at boat noise, we see that there's a few more and then way more in certain circumstances, and then again, only a few more. So we're seeing an interesting trend, but specifically when the boat noise is off, not when it's on. We see a very similar trend with pile driving, where you see more startling when the pile driving noise is off compared to when it's on, especially in the afternoon. And then with wind farm, you start to see something slightly different, where you just have elevated startling, and you have this more often when wind farm is on compared to when it's off. So again, you have wind farm being the odd one out and pile driving and boat noise being very similar. Now, one of the things that might be going on here, at least for boat noise and pile driving, is we know that noise often causes a lot of stress in animals, and that stress can result in increased kind of fear or anti-predator behavior, that you're more likely to startle, or you're more likely to run away earlier. You're more likely to respond to something that's not a predator like it's a predator. But we also know that noise can suppress anti-predator behavior through distraction, because they're so distracted by the noise they don't even notice a predator. but it can also suppress it because there's so much information that these animals are having to deal with that they simply cannot deal with. They can't make a decision. They don't even process properly this behavior, and so they don't show anti-predator behavior. So we think that what might be happening is that the noise is causing an increased stress reaction, which increases the likelihood to actually startle more often or engage in anti-predator behavior. But what might potentially be happening when the noise is actively on is that it's suppressing this heightened response through something like distraction. So that the boat noise off days and the pile driving off days may actually be more similar to what we would see in the population overall. But when the noise is on, we're seeing a slightly different behavior because that is changing their response. With the wind farm, again, we don't know. It might be that there's something about the noise that maybe causes some type of habituation, or it's of a particular quality that means that they're still more able to respond to outside influences and are startling more because of some other way that their brain is dealing with the sound. But again, this would require many more experiments to actually figure out exactly why these changes are happening. But what it does mean is that on basically on non-noisy days, you might potentially, it might be harder for individuals, for predators to catch some prey. And on noisy days, it might actually be easier for predators to catch prey. So when we think about what this actually means, Pacific sandlance availability in noisy environments does actually change based on the noise type. So all types of noise impact behavior, but boat noise and pile driving increase availability, while wind farm noise decreases availability. So we're starting to see that there are actually completely different responses that change predator-prey relationships depending on what type of noise you're actually exposed to. And this is something we didn't see in the quality aspect, where the quality seems to just generally be worse. There's something about the behavior that's decreasing their quality. But when we start to actually look at the behaviors themselves, we're starting to see some subtle differences in how these fish are responding based on the type of circumstance. But I think what we can kind of take away from this is the fact that, well, unsurprisingly, anthropogenic noise is not great for fish. But how different types of noise are affecting these fish and what that means for these predator-prey relationships may actually depend on the noise type and how and where these predators may also be occurring. So yeah, that is my presentation. Let me know if you have any questions. I'm very excited to answer questions. I like questions. So yeah.
Thank you, Nora. If anybody doesn't want to clap out loud, there's a react button at the bottom, and then you click on it, and then you click on a little hand applause. Good old technology times. Yeah, so if anyone wants to ask, yay, there we see some.
Yay.
If anyone wants to ask Nora any questions, you are welcome to like turn on your screen and unmute yourself and like ask her in person. Or if you would, well, not in person on a screen, but if not, you can type it in the chat and I will read it out loud on your behalf. So I see Nathan or Nathaniel has the
Ah.
there we go.
Hi,
Okay,
Nora.
Hey.
I'm guessing you
Um,
two know each other.
yeah, I work in the lab with Nora, but I wanted to come see yeah, what your results are. It's really cool. Thank you. But I was just wondering what you know about sand lance like foraging behavior. Like what do they feed on? How are they detecting their prey? And could like I'm curious, like in your experiments, I'm assuming you were feed like I don't know what you were feeding them, but like in the wild could anthropogenic noise in fact their or impact their ability to like get food themselves and so like maybe further impact their quality and such?
Yeah, so that's kind of one thing I'm interested with this idea with the wind farm being so different is that so specific sand eat copepods, which are very tiny zooplanktivorous little critters. They're very tiny. A lot of them end up just kind of floating in the water, but there's also a whole bunch that will be found on kelp, for example, or other types of wow, I am blanking on the name of the type of organism. Not fungus. Seaweed.
Algae?
We'll just go with seaweed. Thank you, algae. And so we know that a huge amount of the foraging that goes on is just simply in the open ocean, that they'll find. I don't know if I don't think they necessarily go after krill a whole lot, but you do get these clouds of plankton, and we know that they tend, I think, to go towards these clouds of plankton like a lot of the other kind of forage fish end up doing. The interesting thing is we know from other experiments with other types of fish, also fish that eat things like copepods. A lot of these experiments are done on reefs, but we know that a lot of fish will struggle basically processing or finding and catching food. We don't actually know how sandlants find their food because we don't know very much about sandlants at all, or at least not Pacific sandlants. And we don't know much about the processing, watching them eat. So I did feed them. We would do plankton tows every couple of days and dump the plankton into the big systems in Friday Harbor because they have a flow through system. When we were at UVic, we would feed them Artemia a couple of times a day. Occasionally you can see them crawling across the screen of the cameras, which is hilarious. And you can see them swim and feed. So usually when they're swimming, they're just kind of like swimming across the camera. When they feed, they swim, and then they tend to like all kind of disperse and they aren't all swimming in the same direction. And you'll just see them kind of like dart forward and go after the thing. So we assume that they just kind of find them, probably visual, considering how much of their face is their eyes. But so on the one hand, sound could potentially impact their ability to catch, find, and process or eat food, because we know that that does happen in some species. On the other hand, we also know that some crustaceans and other invertebrates are also affected by noise. And I think that there was recently a study that was trying to look at plankton and whether plankton was affected by noise. And I think that they found that they were in some way, although how, I don't necessarily know. But there is a good chance that noise is also kind of basically messing up their food source or their ability to actually eat as well.
Thanks for the question and the good answer. Anyone else? I see Jim turn on. Jim, would you like to go?
Yes. Are you able to hear me?
Yep.
Yeah.
Thank you. I'm wondering if the protection area that I read about that deals with protecting orca and extends over Juan de Fuca Strait out as far as Port Renfrew, or possibly a little bit west of Port Renfrew, swings around Victoria and then up over to the east towards San Juan Island to cover that area, as I believe that protection zone has been in place for a while to protect orca from disturbances such as noise.
Mm-hmm. So I think that protection areas can be very useful, and I know that there's a lot of speed limits and a lot of these types of things in trying to keep boaters and stuff out of a lot of these areas, especially moving very quickly. And it may reduce noise, but it doesn't stop noise. So one of the kind of frustrating things, especially with noise underwater, besides the fact that we don't experience it, so we don't find it particularly annoying, and so we're a little bit less likely to adhere to a lot of those rules, which is something I've definitely seen on the water, is also the fact that noise travels farther and faster underwater. So you will frequently hear any type of vessel before you actually see it, which means in order to effectively massively reduce noise, I think a lot of those protection areas would need to be much, much, much larger than they actually are. And a lot of the kind of the lower frequency or the kind of lower pitch the noise is, the farther it travels. And a lot of the boats, a lot of the human noise that's generated is incredibly low frequency noise. And so I think that the protection areas definitely help, but I think that noise is just pervasive. And as there is more noise, there's simply more noise that you can't entirely eliminate it even from protected areas. One of the other issues is that sandlands are incredibly restricted in where they can actually live because they need very particular types of sand. So there's one massive, what we call a wave field, which is basically like a ripply beach on the bottom of Juan de Fuca Strait. No, San Juan Strait, right near San Juan Island. There's this big wave field, and that's where we think like 90% of the population that is found in the San Juan Islands that's where they reside during the winter at the very least, if not year round. And where we are, we've found a couple of beaches that are potentially really good, or a couple of sandy areas that are particularly good, but there aren't as many, and they're a lot more kind of scattered. And so if they're not in the protection zone, then it doesn't really matter if there's a protection zone. The fish simply can't leave these sandy beaches that they need to bury in. So that ends up kind of complicating it, is that a lot of these beaches are very close to a lot of the shipping lanes. They're very close to a lot of these places that, you know, right next to the shore might be slightly protected. It might be protected even 100 meters out, but that's, you know, compared to how much noise is being spread by a lot of these vessels, there's only so much it can do. But I also don't know as much about noise propagation in the Salish Sea specifically, but I do know, looking at some of the maps, that like if you look at the maps of the noise, even if there's protected areas, there's still elevated noise there simply because there's vessels in this area.
Thank you. Challenging.
Thanks, Jim.
Mhm.
Well, one more person works up the courage to ask a question. I'm going to ask one, because just thinking about like real life scenarios, some of these animals are subjected to multiple like cumulative effects of noise. So did you ever play around with like playing all the sounds or anything like that? Like, and see how that affected, like imagining, I guess, you know, a boat near a boat driver kind of, did you do any of that?
We didn't. So as with most lab and field science, we ran into many exciting situations with equipment and finding fish. But one of the things that actually, one of the reasons we originally just kind of made the experiment the way that it was, is that we wanted to try all of the variations as much as we could before we kind of narrowed in onto what the thing is. So the fact that we're seeing very different responses to these different noise sources in their behavior was kind of what we were maybe not hoping to find, but what to a certain extent I was expecting to find, simply because different noise probably will have different types of effects on behavior, right? So if you have something that's like, there's like this kind of idea that, well, sounds that you can habituate to, like road traffic, like, you know, wind farm noise, something that's constantly going, may actually not be as bad in the long term as something that like suddenly shows up and is loud and then goes away. And that animals may actually be more on edge around a noise that's really intermittent and startling compared to a noise that may be annoying but is consistent. And so we were trying to kind of start to get at like, are we even seeing differences, or is this just, it doesn't matter, noise is noise. So it's kind of exciting that we're seeing differences, but that then starts getting to the question of, if you do have these different noises, well, does one of them take like precedence essentially in their effects? If you did do something like you have boat noise, but all of a sudden you start construction across the way, does this add a whole new thing on top? Or is it just defaults to whichever is kind of worse? Or do you get these additive effects where you're already really stressed and then you add something new on top and everything gets even worse? And that, I think, would be a really interesting place to start going next, and trying to understand the cumulative effects, because that's what these animals are living with. And that's what a lot of times they can't escape. And some of it is like, yeah, we were really trying for noises that are like annoying enough that there's something these animals would potentially live with, but not damaging and not annoying enough that they would necessarily completely leave. But yeah.
Very cool. Yeah. Oh, I have more questions, but anybody else? Okay, I'll go one more time just because you mentioned they're habituating. So the time scale, was that relatively limited? And did you compare kind of beginning, end, or was it just the complications of?
Yeah, so this was a complications issue. So our original plan for this experiment were to have them be 3 months minimum.
Mhm,
You can see that 10 days is not 3 months.
mhm.
So unfortunately, we had a variety of different things going wrong. We had double bookings of equipment. We had other classes coming in that needed to use stuff. So that's kind of one of the exciting things about merging lab and field stuff, is that you have to work on a field timeline, but you have a lab schedule.
Yes.
So yeah, so we couldn't really look at habituation with the dormant population because they were properly dormant. We basically didn't see them until the very end of the experiment, and that was the 10-week one where we actually had kind of the time to start looking at some types of habituation, which also might be one of the reasons we didn't see differences at the end. It could be that there was a period where they would have potentially responded, differently or badly, but then they might have all habituated. So we don't really know if there is something like habituation going on with the dormant population. Um, but with the 10-day experiment, I think different people would potentially argue whether or not an animal could habituate in that time. I would say that some people would say that 10 days is more than enough for an animal to habituate to something like that. And some people would be like, haha, are you kidding me? No, you need at least like 2 months for somebody to habituate to not only a noise, but also coming into captivity. Um, so we did on some of when we were looking across days, we did see some slight changes, where it appeared that what might have been going on is as you got, so a lot of times we had obviously days in a row where they were exposed to noise. So you might have 3 days in a row where an animal is exposed to noise, and then 2 days off, and then another like 3 days. And so with some of the treatments, I think boat noise was one of them, when you had like more days on back to back. So if you had 3 days on, every day you would see more fish in the water column, for example, or higher numbers of fish startling. And then as you had days off, you would see fewer over the days off. So we do think that there is some kind of ramping up and ramping down, but because we had such a limited run, we couldn't really look at this very effectively. And so we couldn't really statistically analyze it very well, simply because we had so few instances of multiple days in a row. So we think things get worse over time in some treatments, but we're not entirely sure.
Thank you. Jim, did you have another one? I saw your mic's on. Feel
Yes.
free. Yeah.
Thank you. As an aside, if you'll entertain this question, related to your comments about pile driving, you mentioned pile driving several times. So it's obviously an important part. And as it happens, right now in the Inner Harbor, Victoria, at the ferry terminal, the new ferry terminal that's being built for the Coho Ferry, there's major pile driving going on. It's the largest I've ever seen, and it's very noisy, of course. So I know it's a different topic, different location, but it would seem, looking at potentials in the future, potential research, given this opportunity, there are, of course, species in the Inner Harbor, Victoria, that would likely be impacted by this. It doesn't happen very often to this extent. Maybe something you want to think about down the road if this ever happens again. It'd be great to take
Oh, yeah.
advantage of this.
Yeah, this would be really cool. I mean, it is kind of one of these perfect examples where you have construction. Ideally, what you'd really want to do is have like a year before and then a year during construction to see what's happening with the animal population. So who's still there, who's leaving, who might actually be showing up, because we do know, I don't know as much of this research in the fish world, but I do know a lot in the bird world, that a lot of times with the onset of noise and with the onset of human disturbance, although you do get a lot of really negative effects on a wide range of animals, you do get opportunists that end up actually doing quite well in these disturbed areas, simply because it's easier to hunt, for example, or you're not competing anymore with like your most important competitor, and so suddenly you have access to all these resources, even though you also have elevated stress. So yeah, I think it would be fascinating to actually do a study and look at species populations and look at how things are changing in neighboring areas that can't necessarily avoid the noise, but are also not close enough to be directly affected by a lot of the construction. I will say the one really good thing about stuff like pile driving, and it's not a perfect solution, but it is potentially a very good solution. So bubble curtains are something that people have been using, where you essentially have 1 or 2 layers of bubbles that are going up. And because the bubbles basically disrupt noise, and so the noise hits the bubble and then it bounces around and it reflects off of a bunch of stuff and just kind of gets stuck in the bubbles essentially. And so it acts as an amazingly good buffer underwater in terms of reducing sound noise. So a lot of pile driving and a lot of other types of construction that are relatively sedentary, like in one spot and don't need a lot of like weird stuff coming in at weird angles, can actually use bubble curtains to massively reduce the underwater noise. Is something that I think not necessarily all construction operations use, but I think more and more and more operations are using as they've proven so effective, as long as the currents are not very strong. So there is some stuff that's like, there's some caveats, but in general, they can be quite effective, especially double curtains.
Thank you. Thanks.
But yeah, that's a really cool idea.
Awesome. Thank you, Nora, for sharing your excitement and knowledge with us. It was a great talk. Well, thank you all for paying attention and being an engaging audience. Next Monday, or sorry, the last Monday of every month is Marine Night. So if you would like to join us, Monday, February 24th is the last Monday night. The Marine Night talk will be about biodiversity and conservation in like the nearshore and the tools they're using it. So I know, for example, they're going to be talking about cameras and this cool new tool they have to study microplastics in the nearshore environments and different conservation things about that. So thank you all. Please tell your friends to come join us. And yeah, thank you again to Nora for a great talk and for everyone's attention.
Yeah, thank you for inviting me and thank you for very cool questions. I always like answering questions, so.
Okay, happy Monday, everybody. Take care. Bye. All right, Nora, thank you again. I really enjoyed your talk. It was really interesting. So that was great to see.
you.
And I'm guessing this is PhD work or
Postdoc.
postdoc. So yeah, very cool. And I hope the rest of it goes well.
Awesome. Thank you very much. And thank you for inviting me. It's very fun.
Awesome. Okay, good. Okay, thank you. Bye.